Bon. Je vais juste voir si ça marche, mais je pense. Vous le voyez, non?
Salut. Oui, on te voit.
Okay.
C'est horrible. Bon, c'est pas grave. Ah.
Bonjour, Reinhard.
Oh.
Bonjour, Reinhard.
Ça, c'est désagréable.
Bonjour. Bonjour, Eva. Bonjour.
Bonjour. Bonjour.
Should I share my screen already?
Already?
No, we have some time. No? Mm.
I will say a few words. Well, you can share your screen. I will say a few words before we start.
Okay.
And then
I can share my screen after. It's nicer.
Okay.
This way we see each other.
The thing is, I have too much background. Anyway. 3 minutes to start?
Perfect.
No? Yeah.
So I should stop at 25 past 4.
Yes.
Yeah.
And then you'll have 5 minutes of questions. 4:59 actually. Ah. C'est une casquette à mon truc, ça marche pas. Okay, I'm going to start. So Welcome to this mini symposium for the conference ICMNS. And this mini symposium is about mean field models in neuroscience. In this symposium, you can ask questions at the end of the talks by raising your hand, and we'd like to have some open discussions. So, and before we start, for those who are not very familiar with the mean field methods, I would say that mean field methods are dedicated to studying the limits of a large number of neurons in interaction, studying the limits and proving the limits, and perhaps sometimes getting some information for the finite size effect network. So our first speaker is Eva Le Charbard from University Paris 1 in France, and she will speak about metastability for interacting neurons. Thank you, Eva.
Thank you, Romain. I will try to put this on full screen. Okay, so now you should have a nice look at it. So thank you for inviting me. So I'm working in Paris 1 in Sorbonne University, and this is a joint work with Pierre Montmarché, who is a probabilist from Paris, on the former Paris 6. And okay, so I start right away. So I will speak about metastability for interacting neurons in a mean field frame. So I start with the N spiking neurons, who are described by the membrane potential values, which are positive. So it's a complete excitatory framework. So I call the potentials XTN1 up to XTNN. And then each neuron spikes at a rate. So there is a jump process behind, which is f of its potential at a given time. And the rate function f is increasing. It's supposed to be Lipschitz. It will be bounded. And this is important, f of 0 is 0, such that if there is no input, there will be no spiking. I will explain that more. And then when one of the neurons spikes, its own potential is reset to resting value. And for convenience, I choose that to be equal to 0. And all the other neurons in the systems, and that's the mean field assumption, get the same additional positive kick to their potential, which is h divided by capital N. So capital N is the size of the system, okay? And in the sequel, I will call this little parameter h. It will have a certain role. I will call that the synaptic rate. So that doesn't evolve in time. So little h is fixed all over this talk. So this is the spiking mechanism. So basically you have to think of, I mean, it's really spiking neurons, and in between successive spikes, we have a leakage effect, and I take that to be at exponential speed. So the potential of the neurons are lost at rate minus alpha times xt in between the successive jumps of the system. So this is a model that I have first seen in papers by Bruno Cessac in discrete time. And then we started working about that together with Antonio Galvez, and started also writing down the mean field limits in a series of papers. The first one with Anna De Masi, Antonio, myself, Enrico Presutti in 2015. Then there is a follow-up paper by Nicolas Fournier. There is a paper by Philippe Robert and Jonathan Toobull. And Quentin will speak about that in the next talk also. Okay, so it's a simple leaky integrate and fire model. And just for those of you who come from the Markov process world, so it's actually a very simple Markov process. It's in dimension n, and it's what people call a piecewise deterministic Markov process. That means the only stochasticity comes through the jumps, the spikes, and in between successive jumps, there is nothing but the deterministic flow, which is describing the leakage of each neuron's potential. So the generator is this one, is a sum of two terms. The second term is the deterministic flow, the loss of potential. And the first one tells you that actually, given the potential values of the neurons, they all spike independently, the one of the others. So the underlying Poisson noise is actually independent for each of the neurons. And then it describes explicitly the jumps of the total system. So the jumps are described by this delta I here, and it's small jumps for all of the neurons who receive the synaptic kick of the spiking one, so the H divided by capital N. But there is the reset of the spiking neuron to 0. And that's why there is a minus xi here. And we call that, you will see that in the last talk of this session by Xavier Ani, we call that the big jumps, which are unbounded, and which are actually the reason why even in the mean field limit, the model will stay stochastic. So for those of you who like Hawkes processes, just to tell you that this process can be seen as a Hawkes process in dimension n. So it's a system of interacting Hawkes processes, which are nonlinear because of the weight function f, and which would have exponential kernel function and the reset to 0, which is an additional feature. Okay. So the system itself for n neurons, since I suppose that f of 0 is equal to 0 and 0 was the reset value just after the spike, this induces actually the fact that the all 0 state is the only invariant state of the finite neuron system. And actually this has been shown first in a paper by Alini Duarte and Guillermo Ost. So if the spiking rate function is only differentiable in 0, that's the only thing you need to know, plus this Lipschitz continuity, then we know that almost surely the system will stop spiking after a finite time, and which means that after the last spike of the total system, it will just relax back to equilibrium, which is 0 here, okay? And the proof of that is actually very easy, but I skip it. And of course, this is only true for fixed finite size systems. So as n tends to infinity, that will drastically change. And this is what my talk is about. So actually, as n tends to infinity, so in infinite limit systems, the 0 configuration will become unstable, at least if we take good values of the set of parameters. And the parameters are the loss of the potential and the input synaptic rate, little h, the kick that you give to the others. Okay, I don't see the first line because there's the zoom, which is hiding that away. But so I just told you that there is a last spiking time, which is finite for the system, after which there is no spike anymore in the system. And this is, of course, kind of natural, because you might have observed that I'm speaking about isolated systems. So there is no outside input of the outside world. So it's an isolated system of neurons. So you can interpret L, this last spiking time, as the time an initial stimulus would survive in the system until its influence just fades away. Okay, and this is a simulation that Christophe Pouzard made in a slightly different version of the same system, where we added synaptic plasticity. And I just put that here to convince you that actually for big N, so the membrane potential is here, time is going on here, this is the residual calcium, whatever. You see that it's attracted to something which is not 0, clearly. So that would be something that we call the metastable state of the system. And I will explain that in the sequel of the talk. So this will be the main part of the talk. So I speak about metastability. Okay, so I try to explain that this state of the state space where somehow the system seems to stabilize is a metastable state of the system and what that actually means. So if you open mathematical papers on metastability, you will see definitions like these ones. It's a transient behavior of the system, so it's something that will not persist in the very long run, but it's a behavior where the system stays a long time close to something that is seemingly a stable point, and that we call the metastable state. And it has been first made rigorous by Leibowitz and Penrose in a Journal of Statistical Physics paper in 1971 by these 3 points. So the first point, if you have a system and a metastable state and you start in the metastable state or close to it, then you're very likely to stay very long in the vicinity of this state. But once you have been kicked out of it, it's also very unlikely to return there, okay? And this kick out, so the exit time of the neighborhood of the metastable state is actually usually unpredictable, and for probabilists, this means that it must be exponentially distributed, okay, if we suitably renormalize this time. So that's what I'm going to show in the framework of the neurons here. You might have seen talks about metastability for small noise diffusions that evolve in an energy landscape like that. So I tried to make a picture here. So this is the energy where the diffusion lives. So you have the minimum of the energy here. So that would be a stable state. And the second local minimum here is a metastable state. And to come from the metastable state to the stable one, you have to cross this energy barrier. And the higher this barrier, the more difficult it is. So this is actually, it's linked, of course, to large deviation theory. And it's the appearance of a statistically rare event. So this overcrossing of the barrier that pushes the system out of the metastable state into the stable one, if there is a stable one. Okay. So of course, for the neurons here, I don't have an explicit shape of an energy, but I will show something similar in the framework of the neurons. Okay, so what I'm going to show is that actually the renormalized last spiking time, so L divided by its expectation asymptotically, so as n tends to infinity, will converge to an exponential distribution. And intuitively, this will happen because during a long time, the system has the impression that it's already in its infinite population limit. And inside this infinite population limit, also close to another invariant state than the 0, 1. Okay. And usually this metastability is shown for stopping times. So stopping time would mean that the event of having observed the last spiking time before time t, that should be something that only depends on the path before time t. But of course, at time t, you don't know if the last spiking time has already happened or not. So it's not a stopping time. We could turn it into a stopping time by considering a slightly bigger filtration, but I'm not going to do that in the sequel. Actually, I will prove metastability for a certain exit time of interesting domains. And these domains will be the first one, that the average weight of the system, of the total system, is above a certain threshold, which I call delta. So delta is something positive. And the second type of domains is to say that the average spiking weight is in the vicinity of the limit n to infinity limit equilibrium spiking weight. Okay, so these two kinds of state spaces, domains of the state space will be considered. And for the exit times of them, I will prove that it's exponential. So depending on the time that remains, I will try to explain you three things, at least some ideas behind them. So the first is what the limit systems looks like. The second, what the invariant states of the limit look like, and then why there will be this exponential distribution. And the main mathematical arguments of our approach will be coupling. I will explain that. And the construction of a simple auxiliary process that will give us a lower bound on the total spiking weight of the finite system, and that is easy to be studied from the large deviation point of view. So I will just give some hints on all these ideas in the sequence. So first of all, the limit system, and that also, I guess, prepares the talk by Quentin. In the limit, as I told you, the big jumps will survive because each neuron, even in the infinite population limit, will continue spiking stochastically according to its own weight. So in the limit, each neuron will be described by a differential equation which is nonlinear, which describes its the evolution of its potential. So we still have the loss, we still have the reset to 0 after the spiking, and then the influence of the system due to the spikes of the other neurons just becomes deterministic, as it's usually in the mean field limit. So it will be h times the average spiking weight of the system at the given time. Okay, so this is a nonlinear system because it depends on the expectation of the spiking rate. but you can show that actually this is well defined under appropriate conditions on the spiking rate. And actually, we even have a control on the difference of the limit potential and the finite size potential of a given neuron if we construct them jointly using the same noise. And this control is given over finite time intervals. And then the speed of convergence is in 1 over square root of n. And this has already been done in the paper by Robert Touboul, in the paper by Nicolas, myself. I guess it's also in the papers by Quentin that he will speak about them. I will cite them a little bit later. Okay. Okay, so this is the limit system. Good. So what about invariant states of the limit system? So whenever you are in an invariant state, that means that it must be stationary, and that means that the average input that comes from the system, so the h times the mean spiking rate, must be constant. So I call that constant just a little b. You consider this as a parameter, and then for each fixed point of the parameter, you just get a classical renewal Markov process. Why renewal? Because you have the spiking neuron, the reset to 0, and each reset to 0 induces a loss of memory property, because, and then you can write down actually explicitly the associated invariant probability measure. For each parameter b, you get exactly one probability measure, pi v, and then you have to solve the self-consistency equation, which just tells you that for the nonlinear equation, the unique or the relation must be that h times p of f, so the mean spiking rate under the parameter b, must equal the parameter. Okay, I guess Quentin will speak about that more. So of course, if we take the parameter b to be equal to 0, that just means the all 0 system is still an invariant state. Of course, that must be like that. And then the main question is, will be there another invariant state? And the answer is yes, if the synaptic rate is sufficiently high. Okay. So, well, it's not exactly only the synaptic rate which is important, it's actually the product of the synaptic rate and the derivative of the rate function in 0, which means that you have a product of what I would call the sensitivity. So this is this third parameter k, which is the derivative of the rate function in 0. Okay, so if the product of sensitivity times synaptic rate is sufficiently big, so bigger than the loss rate, then it's possible to prove it's relatively easy that we must have at least a second non-trivial invariant state for the limit system. And this has been observed by all these people. And actually the second equilibrium is an absolute continuous measure having a compact state space. You can write it down explicitly, except that you don't know the closed formula for the mean spiking rate. Okay. Well, and for the sequel, actually, for the coupling and this loss of memory, actually, we did it in the framework where the spiking rate f, you remember I told you it must be bounded, and actually we did it in the case where it's linear and then saturates, okay? Which is, of course, a very big, well, simplification. We are confident that it would also work for something convex and then saturation, but the saturation is really important. I hope that I have time to explain that. So let us stick to this. So I have weight, so increase of weight k up to the moment when I cross the saturation level, which is this little f star here, which is the maximum. Okay, and this in the sequel of the talk, I will only speak about that. And then we can show in this framework if k times h is sufficiently high, then actually the second equilibrium in the limit system is unique and it's globally attracting at exponential speed. There is this series of papers by Etienne, Quentin, and Romain on the long time behavior of the limit system. I'm not going to speak about that. I will speak about something else, which is a loss of memory property that induces the exponentiality and which is done by coupling. And this coupling will actually imply our main result, which tells us that for these saturating rate functions and for sufficiently high values, of k times h, so the increased rate of the function f and the synaptic rate. We have the following, that the finite system, so for n finite, stays a long time in the vicinity of the limit. What do I mean by limit? I mean actually the limit equilibrium spiking rate that I don't know explicitly, but I know it exists. And then the exit time of this vicinity, which I call little tau here, is exponentially distributed in this sense here. Okay. So the probability uniformly in little t, the probability of overshooting t, if you renormalize by the expectation, that will tend to e to the minus t, which is the corresponding quantity for the exponential function. And we have also an explicit speed of convergence in the system size. Okay. So why the exponential distribution? So actually what we did in our paper is the following. We cut the state space into two parts. So the main part is there where the mean spiking rate, which I call f bar, so it's just the sum over all spiking rates divided by n, is strictly about some small threshold. And then the idea is if the process, the n particle process, has not left this space here after some fixed time, which doesn't depend on n, it's a fixed time, say 1, then this mean spiking rate must be in the vicinity of the limit equilibrium. And once you are in this vicinity, I will be able to construct the coupling and forget the initial position, which induces the loss of memory. So the trials to reach the all zero configuration become independent, and this gives you something like a geometric distribution that converges to an exponential one. Okay, actually, I'm not completely honest here because it's not a vicinity of the true limit equilibrium, it's the vicinity of an auxiliary limit equilibrium that we constructed by this auxiliary process. I try to explain you this here. So actually, all we did is based on the idea to compare the mean spiking rate of the system to an auxiliary jump process, also a PDMP, for which we know the exact large deviation estimate. And this jump process, I can show you the generator. Please don't look at it, but all I wanted to say is that here, the jump terms, which is the blue one, is only of the order 1 over n. So it only has small jumps. So by considering only the mean spiking rate and the lower bound on it, we can manage to consider classical large deviation, I mean classical jump processes for which we know the limit process and for which we have an explicit limit system, which is a deterministic one and not stochastic, okay? And for this deterministic limit system, which gives us a lower bound on the mean spiking rate, we know that there will be a second invariant measure that is attracting, and we will use this attractiveness to couple processes in the limit. I guess I don't have time to speak about coupling, so I just will close with this figure here. So this reproduces basically what I told you before. So I have a big part of the state space, and basically the process will spend all of its time in this big part. This is the D here, where the mean spiking rate is lower bounded by something very small. If we start in this big part of the process of the state space, then after some finite time, I will enter this small one, the red one, where the mean spiking rate is above the limit rate of the auxiliary process, which is a very pessimistic lower bound, but that helps me to couple processes, which means that inside this part of the state space, if I take two trajectories, then I will be able to couple them in a time which is of order n, and coupling means that I really force them to evolve together. And this induces actually the loss of memory that gives the exponential distribution. Okay, so I will stop here. I will just make a last slide. So my phone tells me it's 25, so I have to stop. I just wanted to mention that this is not the first time, of course, that metastability for systems of interacting neurons has been considered. there are other papers by Morgan André. He will speak on Wednesday or Thursday, I guess, in the session of Christophe Pouzat. And there is a numerical study by Mila Brocchini and Miguel Abadí in the time discrete version. Okay, and our paper with Pia is on arXiv, and it has also appeared. And I thank you for your attention.
Thank you, Eva. Do we have, so if you have any question, you can raise your hand. There's a little button at the bottom of the screen, and then I will invite you to speak to Eva.
I was too fast.
So I'm not very familiar with this process. So if I miss some of you, Rainer?
Excuse me. Is it possible that there is kind of parallel situations in classical branching processes where you know when the branching process is critical, then, well, if he's still alive after a long time, then you will be in exponential, you will be close to an exponential limit distribution. And is this a kind of parallel phenomenon, or is this completely false? So
no, I'm pretty
like
sure.
this.
I'm pretty sure it's exactly the same, I guess. I mean, I'm not aware of the theory on branching processes, but I guess it's also linked to quasi-stationary distributions. But of course, so if you have a critical or even subcritical, no critical or say critical branching process, which has not yet died out, then you're sure that you're close to something that looks like a stable. Yes, if you renormalize as you, I think it's
okay. Thank you.
But maybe I should add, because you have mentioned the name critical, no? I guess that all we showed here would be in, of course, there is no direct comparison to a branching process here, but it's if I could compare, then I would say it's the supercritical regime that we have been working in.
Okay.
Because I'm not quite sure that it's really the same framework, because the second...
No, it's certainly not the same framework, but there seems to be some parallelity in terms of metastability.
Yes. Yeah.
Okay, thank you very much.
Okay, there seems to be a question by Etienne. Can you speak? Oops.
Okay, thank you, Eva. Can you hear me? Yes, okay. Can you tell us a little more about your assumption that the rate is globally Lipschitz? So what happens if you take, say, f of x equal to x squared, and you don't use any cutoff?
As you know, the limit, the mean field limit exists and can be proven to be, I mean, all this works perfectly fine. So you want to take x squared and cut it off at some, we need that it's something like concave, Etienne. It's because all I told you, and I even did not really tell you about that, we did the coupling of the weights, and we have to be able to deduce the coupling of the associated processes from the coupling of the weights. And we are able to do that only for concave weight functions. So x squared for our result, I'm not sure I would be able to say something for the moment with the same techniques.
Okay, thank you.
Okay, I think we will stop question and to hear the next talk. So the next talk is by Quentin Cormier. Sorry?
I said good. Nice to see you.
Next talk is by Quentin Cormier, Oscillations in a Mean Field Model of Spiking Neurons, and Quentin is a from INRIA, Sophia Antipolis in the south of France. So I have to. You should be able to share your screen, Quentin, no?
Yes.
Okay. The microphone is yours.
All right. Do you see my my slides?
Yes.
So first of all, thank you very much for giving me this opportunity to present this work. So I'm going to talk about mean field model of interacting neurons. So as Eva mentioned it, this is the same model than in the previous talk. And I will focus on oscillations, so spontaneous oscillations for this networks of neurons. So we consider networks of integrate and fire neurons, which are interacting each others, and under suitable assumptions on the interactions. As the number of neurons goes to infinity, we have mean field descriptions, which take the form of Martin-Vlasov stochastic differential equations. And the questions I was interested in is to understand the long time behavior of this Martin-Vlasov equation, of this mean field description. And we try to take a dynamical system point of view. So we wonder what are the invariant probability measures in the same way that for ODEs, we look at equilibrium points. And we want to decide if these invariant probability measures are stable, so either global or locally stable. So the main motivation of these questions is the study of metastability, as Eva described it, because locally, at least locally stable invariant probability measure of the Martin-Vlasov equations are a good candidate to be metastable state of the finite number networks. And the second motivation is the study of spontaneous oscillations in these networks. So we will look at an invariant probability measure which is not locally stable, and we will see that under suitable assumptions we can prove the existence of oscillations, so of bifurcations of the mean field limit. So the questions we want to answer here is for which parameters the networks exhibit spontaneous oscillations, at which frequencies those oscillations appears, and what can we say about the solution. So I will start by recalling the particle system and explain how we can get the limit, the mean field limit. So then I will talk about the invariant probability measure on the case of weak interactions. So when the interactions between the neurons are weak enough, we have a general result, which is a uniqueness of the invariant probability measure and convergence to it. For stronger interactions, however, this is more complicated, and we have a local, so we will look at local stability. And then I will talk about the main point, which is the existence of periodic solutions near a pop bifurcation. And I will conclude with an illustrative example for which we can, so this is a toy model for which we can compute almost everything. So the model is the following. So we consider capital N neurons, which are characterized by their membrane potential, Vi of t, which lives on R+. And there are going to be spikes, but between the spikes, the dynamics is very straightforward because each neuron solves the ODE V dot equal B of V. And then each neuron spikes randomly at a rate which depends on its potential. So that means that the probability that neuron I spikes between t and t plus delta t, knowing all the past, is equal to f of the I of t times dt. So if you think f to be a non-decreasing function, that means that the higher the potential is, higher the chance to spike is. So then when a neuron spikes, so say the neuron I spike at time tau, then potential is reset to 0. And at the same time, the other neurons receive an increase of their potential by these synaptic weights. So when there is a spike, instantaneously the potential is reset to 0, and the other neurons they receive an increase in their potential, which is given by the synaptic weights between the two neurons. So, for instance, this is an illustration with two neurons. So we have, so in abscissa, this is time. Here, this is the membrane potential. So we have the blue neuron and the red neuron, and you see that at first, each one is living its life independently from the others, solving the ODE v dot equal B of V. And then at some point, the blue neuron is spiking, so its potential is reset to 0. And at the exact same time, the red neuron is receiving a small kick, which is given by the size of the interactions, and then it continues. So to summarize, the model is parameterized by the following. So we have the drift B, which is a function from R plus to R, and it gives the dynamics of the neuron between the spikes. And we assume that bit 0 is strictly positive, such that the dynamics stay on R plus, because when a neuron is spiking, is reset to 0, and then the drift B push you to the right. We have the rate function f, which is a function from R plus to R plus, and we assume that it is non-decreasing, so it encodes the probability for a neuron to spike at a given potential. We have the connectivity matrices and the law of the initial conditions. So we assume that at t equal to 0, all the neurons are identically distributed with an IID probability law nu. So, okay, so now I will take the limit n goes to infinity. So here I do a crude simplification. I assume that all the weights are equal to g divided by n for some deterministic constant g, which was h in the previous talk of Eva. So, 1 over n, this is the scaling of the law of large numbers. So as n goes to infinity, what we obtain is the following mean field equations. So Vt is a membrane potential of a typical neuron in the system. And so it solves, between the jumps, it solves V dot equal B of Vt plus G time expectation of f of Vt. And Vt jumps to 0 at rate f of Vt. So this is this system we want to study, and we want to understand the long time behavior. And of course, the difficulty comes from the blue term here, which is a mean field current, because it depends it depends on the law of Vt. This is a Makin-Blasov equation. So yes, so this model it has been considered by many authors in the past. I can mention the work of Nicolas Fournier and Eva Locherbar, which has results on the long time behavior for b equal to 0. So b equal to 0, it means that the potential stay constant between the jumps. There is also the numerical work of Drogul and Romain, which so they show in a closed setting that there can be oscillation, spontaneous oscillation via up bifurcations. And finally, there is a recent work of Eva and Pierre Montmarché that Eva just presented. So they obtain very deep results for the specific shape of F and B. So what are the first question is, what are the invariant probability measure of the nonlinear process? So fix a constant alpha positive and consider y alpha of t the following Markov process. So this is V is y alpha of t. This is a membrane potential of an isolated neuron subject to a constant current equal to alpha. So this is a Markov process, and we can show that it has a unique invariant probability measure, which is given by this formula. So you see it depends on B, F, and alpha. Gamma of alpha here is a normalizing constant such that it is a probability measure. And we can show that the mean jump rate per unit of time under this invariant probability measure is equal to gamma of alpha. And then the question is, what are the invariant, so to answer what are the invariant probability measure of the nonlinear process, those are the new infinite alpha such that alpha satisfies the closure equation alpha equals g times the mean jump rate, which is gamma of alpha. So the invariant probability measure of the mean field equations, those are this set of measures, which is not necessarily unique. So, however, we have this result for small interactions. So, if the parameter g is small enough, which means that there is a constant g star which depends on B and F, such that for all g smaller than g star, the process, the nonlinear process, has a unique invariant probability measure, which is globally stable, and the convergence to it happens at an exponential rate. And this is obtained by the proof involves a perturbation of the case where g equal to 0. So now, what happens when g is not very small? Well, I will discuss that with two examples. So the first one, we take b of x equal 0.1 minus x and f of x equal x2. So I recall that the invariant probability measures are given by this formula. So what we can do is we plot alpha divided by gamma of alpha as a function of alpha. And if we do that with this example, we obtain this curve. And the conclusion is that there exists two constants g1 here and g2 here, such that for g smaller than g1 or g greater than g2, we have a unique invariant probability measure. But if g is between g1 and g2, we have three invariant probability measures. And numerically, we find that the middle one is unstable, while the two others are locally stable. So another interesting example is the following. We take b of x equal 2 minus 2x and f of x equal x to the power 10. So x to the power 10, this is something crude, such that when x is greater than 1, this is very big. And when x is smaller than 1, this is very small. So we can do the same, but this time there is exactly always one invariant probability measure, whatever the value of g. But if g is between those two values, what we see numerically is spontaneous oscillations. And this suggests that there is up bifurcations for some parameter of g, which is here 0.7. So for instance, this is a simulation with g equals 0.8. In abscissa, this is time. And you see that, so each dot is a spike of a neuron, and you see that the network synchronized. So I will now talk about local stability of an invariant probability measure. So for that, we need to define a distance on a probability measure. And here, this is the total variation distance with weight 1 plus f squared. And we say that nu infini alpha, an invariant probability measure of the nonlinear equation, is locally stable at rate lambda if starting from any probability measure nu close enough to nu infini alpha, the nonlinear current converge to the good values at an exponential rate. And now the result is the following. We can characterize completely the stability of an invariant probability measure nu infini alpha. For that, we need to define this function theta of t, which is obtained by integrating against the nu infini alpha the following function. So d divided by dx of rx alpha of t, and rx alpha of t, this is the jump rate of an isolated neuron which receive a constant current equal to alpha and which start at potential x at time t equal to 0. So at t equal to 0, we start from x, and then we look at the mean jump rate at time t, and we take the derivative with respect to x, and we form this function. And then we can prove that the stability is given by the Laplace transform of theta. So when those zeros are those solutions, if the complex solutions of these equations are all located on the left half plane, we have stability. So in other words, the stability is given by the location of the roots of an holomorphic function. And this result is interesting because the function theta of t, it is only given by an isolated neuron. It is given by the Markov process y alpha of t. So there is no longer Makin-Vlasov process. And we can prove that this criteria is satisfied if f plus b prime is positive. So if f plus b prime is positive, we can prove that any invariant probability measure has to be locally stable. So now I can talk about periodic solutions. So I come back to my example b of x equal 2 minus 2x and f of x equal x to the power 10. And we compute the zeros of the functions which give the stability. So we have algorithm for that. And so if g is equal to 0.5, all the roots are have a negative real parts, so we have stability. But then if we increase g, at some point, we have a pair of imaginary zeros. And so we can no longer decide if it's stable or not with the last theorem. And if g is increased even more, you see that the zero crosses the imaginary axis. And so here is a more complex pictures where we so in abscissa this is the value of the interaction coefficient g. And for each value of g, we report the mean number of the mean number of spikes or the nonlinear current. And the black curves, it corresponds to the invariant probability measure. So when it's dot, it means that it's unstable because here and here we have two up bifurcations. And if g is between those two values, we have a periodic orbit. And we can compute, for each value of g, we can compute the maximum amplitude of this value and the minimum amplitude. And we find this curve. So now what we want to do is to zoom around one of these 2 points around off bifurcations and to prove the existence of periodic solution. So for that, we need some spectral assumptions. And if you are familiar with the classical theorem for up bifurcation in a deterministic system, you will see that you will not be surprised by those assumptions. So we consider an invariant probability measure nu infini alpha 0. We assume that we have a pair of imaginary numbers. So alpha 0 is taken such that we are exactly at the off bifurcations. we assume that those zeros are simple zeros of the holomorphic functions. We assume that those are the only zero on the imaginary axis. And finally, we assume that as alpha varies, those zeros crosses the imaginary axis with non-vanishing speed. So if I come back to the pictures here, you see that when alpha increases, here the zeros cross the imaginary axis with non-vanishing speed. And under those assumptions, the result is the following. So we have the existence of a curve of periodic solutions parameterized by V. So in other words, we have the existence of a family of densities nu V, of probability measure nu V, such that for each V, nu V is 2p tau V periodic. And this is the solution of the Makin-Vlasov equation. And what can we say? Yes. So when V equal to 0, the curve goes to the invariant probability measure nu infini alpha 0. Those periodic solutions are unique in the neighborhood of nu infini alpha 0. Up, of course, to a translation, because if you have a solution and if you translate it, it's remain a periodic solution. And V is the amplitude of the first, yes, so V is the parameter of my family, but it is also the amplitude of the first harmonic of the solution. So if you want, V is the amplitude of the periodic solution. Okay, so now I will conclude with a simple example for which we can compute everything. So you take b of x equal m minus x and f of x equal 0 if x is between 0 and 1, and 1 over beta for x greater than 1. So we have a threshold effect, if you want. When the potential is less than 1, there is no spikes. And when the potential is greater than 1, there is spikes at rate 1 over beta. And what we can do is that if we do the correct change of variables, which is the following, then the equations which give the stability of an invariant probability measures, we can show that it is given by these explicit equations, which depends on delta, omega, and beta. And for this equation, we can do all the computations, and we can check all the spectral assumptions of the theorem. So, for instance, in this, we can compute all the up bifurcations, and this is a parameterized curve, it is a parameterization of all the up bifurcations, all the imaginary roots. So you see that there are many up bifurcations if you choose correctly the parameters. And what we can do is we can look at what happens when beta goes to 0. So this is the limit here. And when beta goes to 0, so we find the first up bifurcations for this value of G0. And we can compute explicitly the period as a function of the parameter m and beta. Okay, so to conclude, we have studied the long-time behavior of Makin-Vlasov stochastic differential equations. When G is small, we have the general result, which is a relaxation to equilibrium. When G is larger, we need spectral conditions to study local stability. And then we can study the existence of periodic solutions near an unstable invariant probability measure that is up bifurcation. If you are interested, you can look at the two papers on arXiv. Thank you.
Okay, thank you, Quentin, for your talk. So if you have any questions, please raise your hand and will give you the opportunity to talk. Yes. Oh, we have Abed. Can you speak, Abed? No.
Can you hear me now?
Oh, yes. Yes, we can.
Okay. Yeah, I have a very, very simple question. Basically, so you talk about the invariance, and the invariance somewhat is related to your connectivity or to your J. So can you just give an intuition, like invariance with respect to what? Is it with respect just to the connectivity, just some intuition about that?
Yes. So what we mean by invariant probability measure, it means that this is invariant by time. So that means that if the population is taken under this invariant probability measure, then as time evolves, density does not change.
Eva, can you speak?
Yes.
Okay.
So my question, but I probably already asked that. What are you able to say if 0 is an equilibrium of the flow? So if B of 0 is 0, or just
yes, that's a good question. So if B0 equal to 0 for local stability, this is not really a problem. So because if you consider what I call the non-trivial invariant probability measure, which is the non-Dirac one, because I do everything locally in the neighborhood of the invariant the non-trivial invariant probability measure, this is not an issue that f of 0 equal to 0. However, when I was looking at global stability, this might be problematic because if you take, for instance, f of x equal x2 and b of x equal minus x, we can prove that for G large enough, no, sorry. Well, no, I'm not sure. This should work the same, I think. Yeah.
and for the oscillations, I mean for this.
For the oscillation, it's not a problem because again, it's locally around the invariant probability measure. The only problem is when you do some global stuff, I think.
Okay.
Okay. I don't see anything on the chat. Okay, well, thank you again, Quentin, for your talk. We'll stop here and have the next speaker, who is Algour Taher from INRIA in France. And we are a bit early on the schedule, so we're going to wait something like 1 minute before we start, and then maybe you can share your title page by
of course.
time. And,
you see everything, my mouse, the screen?
Yes, seems to work. Okay. We'll resume the session. So our third speaker is Algu Taher. He will speak about exact neural mass model for synaptic-based working memory. So the microphone is yours.
Thanks a lot, Romain. Thanks for the organizers for inviting me to this session. I think my talk is a bit less theoretical than the previous one, but more towards application. And the application is specifically working memory. So I will start by explaining what is working memory and how the model is able to model these working memory mechanisms. Working memory, first of all, is a cognitive system. It allows us to perform goal-directed behavior. So let's say we want to achieve a desired goal, and for this, we have to solve a task. This can usually require information to be rapidly stored and maintained, also to be processed and to be rehearsed or to read out. And experimentalists study working memory mechanisms in so-called delayed response experiments or tasks. So basically, they train a subject, it might be animal or human, to solve a task. And during the solving of this task, they perform electrophysiological measurements. So, for example, using electrodes to measure spike trains or local field potentials, LFP. Or with humans, for example, using electroencephalography, EEG, using these cap with the electrodes on the scalp. And these type of experiments in the last decades have led to many theories, and one particular one which I'm interested in is the synaptic theory of working memory by Mongillo and colleagues. And this synaptic theory of working memory, the base concept which is storing the working memory information is short-term synaptic plasticity, STP. It basically comprises two effects which are known as depression and facilitation. And the idea is that the presentation of some working memory information, like here, triggers depression and facilitation, and that the information is maintained and stored in the state of the synapses. And in this model, the working memory information is encoded in a macroscopic state. So not in the microscopic state of the single neurons, but in the macroscopic state of a population of neurons. Of course, if we want to study working memory, we can take a network model like here in the work of Mongillo and perform the simulations and see how the working memory mechanisms work. But since the information is stored in the macroscopic state, it would be nice to have a macroscopic model, low-dimensional model, so to speak. And we wanted to fulfill some properties. Of course, it must be based on STP. And the second thing is it should somehow give access to measures or to some correlates of local field potentials or EEG signals. So let's go to the model. The model is consisting of a network of quadratic integrate and fire neurons, the QIF neurons. So we see the quadratic term in the differential equations for the membrane potential dynamics. This eta I is some constant current depending on the index, and the neurons in the network are coupled via instantaneous synapses. The synaptic current is proportional to the firing rate of the population, and this J is some synaptic weight. The firing rate is simply given by a superposition of all spike trains. Then we have some reset rule, and overall in the network, we have n equations. Taking this type of network, making some assumptions on the eta I, we can perform a mean field limit. So sending n to infinity and also the threshold to infinity. This second limit helps us to render the QIF neuron identical to a phase oscillator model, which is the so-called theta model. And in 2008, Ott and Antonsen published a work which allows for a certain class of phase oscillator models an exact mean field reduction from microscopic dynamics to macroscopic dynamics, so towards a low-dimensional system. And exactly this limit has been performed by Montbriot, Pazo, and Roxin in 2015. They described this, the exact firing rate equations, which I also call here neural mass in this talk. They basically consist not anymore of n equations, but only of two equations, describing one of them describing the mean firing rate of the population, and the other one the mean membrane potential of the population. And the interesting thing here is that this model is exact, the limit is exact. So in the limit n to infinity, this neural mass model, the collective dynamics which we get from the neural mass model is exactly the same as the one which we would get in the network. Of course, in reality, if we want to simulate the network, we will not be able to simulate infinitely many neurons, so we will have finite size fluctuations compared to the neural mass. However, this model is extremely useful, and to apply it to working memory, we, as I mentioned before, we have to implement short-term synaptic plasticity. I will explain it briefly. It refers to two effects which change the synaptic weight between neurons in time. These two variables, x and u, they account for two effects known as short-term synaptic depression, which is weakening of the synapse. So for example, if we see firing rate time trace here, the population is firing, the coefficient x goes down, and it recovers on some time scale of, in this case, 200 milliseconds. Facilitation is the opposed effect. It's a strengthening of the synapses. So neurons fire, U goes up, and then it decays, but it decays on a longer time scale, at least in the prefrontal cortex. Probably you're a bit surprised by this type of STP. Usually we would want to have depression and facilitation to be driven by individual neuron spike trains instead of the firing rate of the population. But this comes, of course, with many problems in performing the mean field limit. And in fact, for the application towards working memory, we don't need it, as I will show you. So we stick with this STP model implemented already on population level. These are the two systems, the network and the neural mass, and we can straightforwardly add the two STP equations to the network and the neural mass. And the limit remains exact. So in the network, we have n+2 equations, and in the neural mass, we have 4 equations, and you see that the synaptic weight here is multiplied by these two coefficients, x and u. To exemplify a bit the exactness, these are network simulations results, first of all, just a network, using a single excitatory population. We see here a spike scatter plot of a subset of 2000 neurons. This is some stimulation current injected into the population, these two rectangles. This is a firing rate resulting from the network, and these two variables are depression and facilitation. The two cases, they are just using slightly different parameters here. After the two pulses, the system goes back to equilibrium, and here it lands on a limit cycle. The external current here applied to the population, it triggers a series of population bursts. You see it also in the firing rate. And if we look at working memory, this series of population bursts is very important for the encoding of the working memory information. But before I get there, I would like to show you how the neural mass performs. So only using 4 equations, and this is these Docker curves which we see here, and we see the perfect agreement on the left side with all the dynamic variables calculated from the network and the neural mass. On the right-hand side, we see some differences here. This is due to finite size fluctuations, because simulating the QRF network can be quite tedious and tricky. I would like to talk a bit more about these, the series of these bursts. We studied this in a different project. I will not talk about it too much. We studied how these type of bursts emerge in these next generation neural mass models. And we studied it using a slow-fast approach, so techniques from singular perturbation theory. We find very peculiar behavior, which is related to the additional timescales, which we include due to plasticity. Exactly. And so far, this was a single excitatory population. That's not enough to study working memory. So we will go towards a more complicated architecture, network architecture, which is still minimalistic. The basic idea is that if we want to encode working memory items, we take one excitatory population to encode one working memory item. So in this case, we have 2 excitatory populations, blue and orange, and they code for, each one of them codes for exactly 1 item. They are both coupled to a common inhibitory pool. We have recurrent connections of all populations, and only the excitatory to excitatory synapses exhibit STP. IB is some background current common to all neurons, to all populations. It's basically a control parameter, putting us in different regimes for the mechanisms of working memory. IS is the external current which we can use to stimulate the excitatory population, so to speak, to load working memory information into the population. And how this works, I can show you in the next slide. So this is at the background current of 1.2. We see the scatter plot of the blue population and of the orange population. We see the currents applied to the blue and orange population. This kick here to the blue population corresponds to applying a stimulation into the network, into the blue population. And this corresponds to loading the information. And why that is, I will show you. This first rectangle pulse is targeted. It's targeted only at the blue one. So orange receives nothing, while the second one, it can be seen as some sort of unspecific readout signal. It is applied to both populations, but only the blue one emits one of these synchronized bursts. We can calculate the firing rate using the network simulation, and we can also look at the depression and facilitation variables. What happens is basically that this rectangle pulse induces depression and facilitation. The information remains stored in the facilitated synapses, but only for the blue population, since it's the only one where we loaded the item. So when we apply the second current, only the blue one has facilitated synapses and emits this population burst. The second case, by the way, again, you see here the darker curve and the shaded curve. These are network versus mean field results, and we see, again, the perfect agreement. On the second column, we see a different working point. The background current is 1.5. We again apply a rectangle current to the blue population, but that's all the current we apply. And what happens is that the blue population starts emitting these bursts, these population bursts, in a periodic manner. So it's on a limit cycle. Here, we reduce the background current and it goes back to its initial state. I will focus a bit more on the right-hand side here, because this is the type of working memory suggested by Mongillo. It is based on these population bursts. So every time there's a burst, facilitation and depression are refreshed, and then after some time, spontaneously, another burst emerges, and this continues forever. Okay. So this has been already done by Mongillo and other people using network models, but in this case, we have an exact limit. So we can use numerical bifurcation analysis to study how these different working memory states emerge. I will not go into the details, but at the basis is basically metastability between different states, between equilibria, between limit cycles, these green ones, for example, which emerge at this half bifurcation. So far, we have seen good agreement between network and neural mass, and the dynamics regimes become clear via the bifurcation diagram. But we can do much more with this mean field model. And I will focus on this case to show you what I mean. Let's talk about the importance of the average membrane potential, VK. You see the time trace here for the simulation, which I have just shown on the right-hand side. What is VK? Well, the network model is deterministic. There's no stochasticity. So in the n to infinity limit, we don't have any microscopic fluctuations remaining. So if we see oscillations in the voltage signal, mean voltage signal, they must be of collective nature. The voltage is nothing else than an electric field potential. So these oscillations can be seen as waves of the electric field potential. And therefore, they're easily comparable to EEG and LFP signals. So let's take some experiments of working memory where we see such signals. The first one I want to talk about is about LFP measurements in the prefrontal cortex of monkeys during working memory tasks. So basically, the monkeys are trained to recognize certain pictures on a screen. And after the training, the experimentalists measure the LFP. Here we see the firing, the spike rate. During the presentation of one object, it goes up. Here, during a second object, it goes up. But what is more interesting is the spectrogram. So this is basically showing the intensity of signals in different frequency bands as a function of time. There are two characteristics here. Every time an object is presented, we have a signal in the so-called delta band, and around 2 to 4 hertz. And also we have this sustained activity in the beta band around 32 hertz. Now we can take this voltage signal of our mean field model, of our very simple mean field model, and calculate the same type of spectrogram. And what we see is a quite remarkable resemblance of the experiment. So we present the stimulation, we have the delta band signal, and again, we have this sustained beta band signal. We can do a bit more than in the experiment because we can calculate the spectrogram separately for the excitatory population, for the inhibitory population, and we can see that the delta band is empty in the inhibitory population. So we can claim that the delta signal here or here is due to the activity of the excitatory population, and in particular these population bursts. The second experiment is with humans using EEG measurements. The type of experiment they perform is they use vibrotactile stimulation on the fingertip. So they put a device on the fingertip, which is able to produce different frequencies. And the subject can distinguish between different frequencies. So they can know if it's lower or higher frequency. The different frequencies basically correspond to different working memory information. So you see here a base frequency F1, a base frequency F2. And again, we see the spectrogram. During the first stimulation, we have this delta response. We have this very broad band response, like also in the simulation, and then we have the sustained beta band activity, like in the simulation. We were wondering if this new model is advantageous compared to other established models. One of the most established and widely used rate models is the Wilson-Cowan model. It's of heuristic nature, and it only describes the firing rate of neuronal ensembles. and also, of course, additional synaptic variables if you want to implement it. This phi is an input-output relation. So depending on the input, we get some influence on the firing rate. And in 2017 and 18, there were two works which have chosen this phi to be in such a way that the state space structure is maintained compared to the model which I'm speaking about today. So we can use a Wilson-Cowan type model, but maintaining the same bifurcation structure. This helps us to make a direct comparison of the new model versus the Wilson-Cowan model in the same numerical experiment setup. So in this one, by loading one item into the blue population. We can use this Wilson-Cowan model and perform the simulation. We see qualitatively similar behavior. So during the stimulation, the fire rate goes up, and afterwards we have these type of population bursts. So in fact, the item is loaded and it's quite comparable. But what is missing are these tiny oscillations on the population bursts. And if we calculate the spectrogram, we see exactly an empty beta band. Not like here, where we have this sustained activity. But if you remember this beta band, it was quite essential in the experiments. So the Wilson-Cowan model is not able to reproduce this. Due to the lack and detail of modeling spike synchrony. Okay, this was all about loading one item in the network, but if you remember, the architecture which I showed you is able to load two working memory items. And this is what I do here. So here, the blue population is stimulated. It lands on this limit cycle, where it periodically emits these population bursts. And at a later time, the orange item is loaded by another kick of same size and amplitude. And then what happens is a bit interesting. The blue population remains on its limit cycle, but also the orange one enters the limit cycle, and they continue to emit these population bursts in an antiphase manner. So, tuck, tuck, tuck. This is, I think, known as memory juggling. And these are network simulations and neural mass simulations, but the network simulations are quite tedious. We can use the neural mass to investigate it in a systematic manner. We have done this. I will just exemplify what we did. We use different amplitudes and durations of the second pulse, of the second stimulation pulse, and try to find out which item remains in memory. In this case, where the orange pulse is very short, it is not able to load the orange item into working memory, while the blue item just remains untouched. In the second case, it corresponds to what you see on the right. Both items land on this memory juggling state. And the third case, the second stimulation is too long. It perturbs the memory state of the blue population. It basically stops emitting the bursts, but the orange one remains. Okay. We can go towards more elaborate network architectures. In fact, we have built a network which is able to hold 7 working memory items. Similar work has been done in 2017 using a Wilson-Cowan model. I show you how it works. So we basically have 7 excitatory populations in the network, each one coding for 1 working memory item. And we stimulate these populations with a series of stimulation currents. First of all, we stimulate the blue one, then the orange one, and then the green one in this case. And every time we stimulate one, they land on this cycle where they emit periodically these population bursts. Here, blue and orange, here, blue, orange, green. We can represent this in a bit easier manner by making a scatter plot of the bursts, of the population bursts. So we put every time there's a population burst, like here, a dot on a line, and this is the population index here. So we see here the cycle consisting of blue, orange, and green. This means all these 3 items are in memory after stimulating them. We can go beyond what we can do with the Wilson-Cowan model, as I have shown previously, looking at the spectrogram. In fact, we can now characterize the neural oscillations during the working memory maintenance here. This is a spectrogram resulting from these simulations. It's a bit complicated, but if we have a closer look, we can understand it. First of all, as in the experiments, we have this delta band response every time we load an item. So that's nice. Then we have strange lines here. Apparently, there are multiples of some base frequency. And this base frequency is related to the longest period in these memory cycles. So basically the period between population bursts of a blue and again a blue. So this time between these 2. And we see all harmonics of these. These are these lines. But some of the lines are more intense. And this is due to the fact that we have additional timescales. For example, the time between bursts of different populations. And these lines are in resonance. So the base frequency F cycle is in resonance with the burst frequency. And this way, this band becomes much more intense. Additionally, as a last point, remember we had sustained activity in the beta band around 32 Hertz, and it happens to be that this exactly hits one of the multiples of the F cycle and F burst, so this is the most intense line here. We can go on with this and try to load more than 3 items, like here, 6 items. So blue is loaded, it lands on the cycle, then orange, green, red, purple, and in this state we have all 5 items in working memory. And then when we load the 6th item, it also lands in the cycle, but then working memory item 5 is lost. So what we see here is basically a capacity limit of this network. We cannot go beyond some certain number of items. And to figure out in a bit more precise what this limit is, to study it systematically, we can use this neural mass model and check how many items remain in memory after some time when using different presentation rates. So using shorter or longer times between these item presentations. And this is what you see here. So we have presentation rates from 1 to 80 Hertz. The orange dots correspond to slow presentation until up to 9 Hertz, I think. Yes. The blue one to fast presentation. And we see here the number of items which remain in the memory. And we see the maximum is 5. We can also see which serial positions are more likely to be retrieved, depending on how fast we present the items into the network. And what we see is a very well-known primacy and recency effect. So if we present the information very slowly, the first items are forgotten because it's a long time ago that the network saw this information, but the latest one are very probable to be retrieved. And for very fast presentation, we rather remember the first items to be presented and also the last item. This is a primacy and recency effect. The similar work has been done using the Wilson-Cowan model. They also have found an analytical estimate for the capacity, and we did an analogous approach. We came up with this expression for maximum working memory capacity. And if we put on the good values, we obtain 4 to 5 items, which is in good agreement with recent experimental results, as well as with, I think, our everyday life experience. The last thing I want to talk about is a work from 2004, where experimentalists have found a predictor for the maximum working memory capacity in the following way. We see here time traces of some voltage membrane potential difference or local field potential difference. It's experiments with humans, as far as I remember, and the subjects see arrays on the screen which show different number of items. So the blue trajectory here shows the voltage trace when two items are presented, the green when 4 items are presented, and the red when 6. What we see when 2 are presented, the curve is quite low. When 4 are presented, it's higher, but when 6 are presented, it does not go further. And this is due to the memory capacity limit to be reached, which is around 5. So we see saturation of these potential difference when the capacity is reached. And if we go beyond 6, so here 8 and 10 are additionally shown, we don't not only have saturation, but the potential difference decreases even. And we try to find a similar measure using our neural mass model, which is this delta V here. And we can do the same type of experiment by showing different number of items to the network in the simulation. The blue curve corresponds to 1 item shown. The orange curve corresponds to 2 items shown, and 3, 4, 5. And we see a similar increase as here, as the more items we present. The bottom panel corresponds to the bottom panel here. So we show 2 items, 4 items, 5 items, and 6 items where we get the first saturation, and then 7 items where we get the decrease. So somehow we can find a similar predictor for the working memory capacity as in the experiments of 2004. This was the last experiment I wanted to talk about, and with this I can conclude. Of course, many of the results which I have shown have been already obtained using microscopic networks, leaky integrated fire networks, and with synaptic plasticity. But the good thing here is that the model is exact and is still able to reproduce the working memory mechanisms when we implement STP. It is low dimensional, so it's very easy to study. We can make systematic scans. We can make bifurcation analysis. We can do a bit of analysis. As you have seen, we could estimate the working memory capacity. a very important aspect is the better agreement with experimental results, because we have seen that this beta band activity is absent using Wilson-Cowan type models, but here, since the Montbriot, Poisson, and Roxin model captures spike synchrony, we are able to reproduce those. And finally, all these advantages are based on the fact that this limit is exact. And with this, I thank you for your attention. This is the publication where these results are from, and I'm happy to take your questions.
Okay, thank you very much, Algold. Let's see if somebody raises his hand. Oh, yes. So we have two questions, one by Etienne, one by Quentin. I'll start by Quentin.
Okay. I have a question concerning the model. When you consider a finite number of neurons, I was wondering what is random and what is not in the model.
There's no randomness in this model.
So maybe the initial condition is taken at random?
No. We start in the fixed points. I mean, we start the simulation, we let the transient pass, and we end up in a fixed point. And this is the starting point of these numerical simulations.
Okay.
What can be random is the distribution of the eta I currents, the constant components of the currents applied to the neurons. In this case, they are Lorentzian distributed, but not random. There's a deterministic way of distributing those Lorentzian.
I see. Thank you.
Pleasure.
Then we have somebody called G Palm. Can you?
Yeah. Can you hear me?
Yes, we can.
Okay. Yes, I just have a question to the beginning when you put your model together.
Mm-hmm.
And I think it was transparency number 6.
I will share my screen and we see.
Yes. I was wondering, I mean, so when you introduce your neural mass idea,
mm-hmm.
you start with n+2 equations.
Yes.
And maybe you said something about it. Why n+2? Why not n plus n squared or something like this?
Why not 3n? Okay.
No, why not even more, right? You have.
I see. Okay. I can explain it a bit. This type of synaptic dynamics is called presynaptic depression and facilitation in this case. So the reason why these X and U reduce and increase depending on the state of the neuron itself, depending on calcium levels in the synaptic terminals. And this is identical for all synaptic terminals.
Yeah,
I'm not
but
sure
why?
So,
I mean, in reality, it would not be identical to all synaptic terminals.
well, this is okay. I can tell you this is a Zodic-Pavlitic Makra model. They assume that it is identical. Of course, it would be neat to have n squared to have one equation for each synapse, but I think this type of mean field limit will be very difficult to obtain.
But it could be that even in that case, if you go to the limit, it could still become 4 equations.
If we what?
Well, if you don't start with this kind of limit behavior already,
Yes.
concerning the synaptic depression and facilitation, and so you start with more equations, it could be that when you go to the limit with the activity, you also come to a limit with the depression and facilitation, and you end up with 4 equations again.
It is.
But maybe with slightly different ones.
It is possible, but I think there is a bit more behind. I can show you. I can show you the case where we have 3n equations, not n squared. for the synapses. So each neuron has 2 synaptic equations instead of the whole population. In this case, we were not able to obtain an exact limit. I know that other people are working on it, on approximations of this mean field limit. I think Thilo Schwalger will be talking a bit about this on the session on Wednesday. And they use some approximation and they end up with more than 4 equations. So I think without the approximations, if there is a way to obtain a mean field limit an exact way, I think it will be more complicated than 4. This is my feeling.
Okay.
But I cannot tell you for sure.
Thank you.
Pleasure.
Okay, thank you, Elgood. I'm afraid that this is the last question. So the last speaker of the day is hopefully is able to speak. Xavier Erny.
Let me share my screen. Normally it should be okay.
Yes, it works.
Okay, in full screen?
Yes, seems like it. So our last speaker is Xavier Erny from Université d'Evry. So it's in the Paris neighborhood in France. And he will be speaking about conditional propagation of chaos for mean field system of neurons.
Okay, so thanks for the invitation. So this is a joint work that I've done with my thesis directors, which are Eva Lecharbar and Dasha Lukianova. So in the first time, I will present you the model of a neural network, which is very close to the one that was shown by Quentin and Eva, with still a huge difference. And the goal of this talk is to prove the convergence of this network as the number of neurons goes to infinity. So let me begin by recalling some basic properties of neural network, just to explain what the model takes into account. So here we assume that the neural activity of a network is characterized by the spike times of the neuron. So for each neuron, we model the set of its spike times by a point process, and we define as a random set of positive numbers. And as you probably already know, the spike rate of a neuron depends on its potential. And each time a neuron receives a spike, its potential is modified. So this is basically the interaction that we want to model. So to model a network of n neuron, we model it by a system of n point processes. So for each neuron, we define a point process Zni, which counts its spike times, the number of its spike times. And we assume that each point process admits a stochastic intensity of the form f of xni. So this intensity is the spike rate of the neuron I. And this process xni models the potential of the neuron I. And in the models that we'll talk, it will be solution of a stochastic differential equation with jumps directed by the point processes Z and J, which is exactly the same framework as the one presented by Eva and Quentin. So the kind of equation that we look is this one, with typically 2 kind of terms. So the first kind of term are the drift terms that will model the dynamic of the potential xni when there is no spike in the network. And there will be a jump term that will model the effect of the spikes on the potentials. So here, for example, when a neuron J sends a spike to a neuron I at time t, what happens exactly for xni is that at time t, it does a jump of height ujit. So this uji can be seen as the synaptic weight between the neurons J and I. So the question that we'll that want to study in this model is the question of the convergence of the system Xn as the number of neurons n goes to infinity. So to study this kind of question, we need to rescale this sum in red to avoid it to explode and to force it to converge. So as far as I know, there exist 2 kinds of scaling that can work to make it converge. So the most natural one that we have seen in the previous talk is the linear scaling in 1/n. So this is the convergence result with this scaling corresponds to some law of large numbers type result. So this scaling will be studied in a lot of models. Here I've written 2 references that are close to this equation. So the first one is an article of Delat, Fournier, and Hoffman about Hox processes. And the second one, an article of Chevalier, Duarte, Lecharbar, and Host that is really close to this equation, except that the static weight does not depend on time. And the other scaling in which will be more interesting in the following is the diffusive scaling, that is 1/square root of n, to recover some central limit theorem. So with this diffuse scaling, we need to consider the synaptic weight to be random variables that are centered to be in a CLT framework. So this model that we have also studied with my study directors, but I won't speak about this model in this talk, but another model that corresponds to this model with the reset jump term, well, with the reset jump that we have seen earlier in the previous talks. So, and the goal of this talk is to study this model with a reset jump in the diffuse scaling. But in the first time, let me explain how it works in the linear scaling, just to see the basic property of the model. But this model has still been explained earlier, actually. So what's interesting in this kind of equation is that it is natural for a neural model, because it can be interpreted in the following way. So here, this drift in minus alpha x means that each time, well, when a neuron doesn't receive any spike, its potential goes by itself to 0 at exponential speed. So here 0 is assumed to be the resting value of the potentials. Then we have a small jump term. So here we speak about small jump because the height of the jump vanishes. So this small jump describes the effect of the spikes of one neuron to the potential of the others. Because you see that x and I does a small jump when the neuron I receives a spike from another neuron j different from I. And then the last jump term, which is a reset jump term, describes the effect of a spike of one neuron to its potentials. Because what happens exactly when the neuron I sends a spike for the potential x and I is that x and I does a jump of height minus x and I. In other words, it jumps to 0. So this models the repolarization of the neuron. So this equation has been studied by Asarazeno, these references. So the two first ones study exactly this equation with different kind of questions. And the third one study a generalization of this equation in a Makin-Vlasov framework. And the goal of this talk is to speak not about exactly this model, but the same model in the diffusive scaling. So the difference is in the small jump term. So here the scaling is in 1 over square root of n, and there are these random centered variables that are here to be in a CLT framework. So in the following, we don't know the distribution of these random variables. So we assume that nu is a law on R that is centered with a finite third moment. And we will note sigma square its variance. So the dynamic of x and I is still easy to explain, very similar to the previous one. So as long as there is no spike in the network, the dynamic effect of x and I is just directed by its drift, by alpha x. So x and I evolves as the function exponential minus alpha. And when there is a spike, there are two possibilities for x and I. Either the spike comes from another neuron j different from I. In this case, x and I does a small jump. So now the height of the small jump is of the form ujt over square root of n, where j is the neuron that has emitted the spike, t is the spike time, and n the number of neurons in the network. And the second case is if it is the neuron I that has emitted the spike. In this case, x and I jumps to 0, as we have seen before. So the goal of this talk is to prove the convergence of this system xn as n goes to infinity. So before proving this convergence, let us explain how the limit system behaves using some heuristics. So what we can observe in our equation here is that the only term that actually depends on n explicitly is a small jump term in blue. So the goal of the heuristic is to study this blue term. To do this, we introduce this process mn, which is more or less the same. The only difference is one index in the sum. So basically, if we manage to prove that mn converge to some limit process that we will note m bar, we will know that the blue term here will converge to the same limit process m bar. And so the limit equation should be this one, which is exactly the same as the previous one, except that we have replaced the blue term by its limit. So here the goal of the heuristic is to determine an explicit expression for this process m bar. So to begin with, what we know about Mn is that it's a discontinuous local martingale whose jump height vanishes as n goes to infinity. So its limit, if it exists, is a continuous local martingale. And so it can be written as a stochastic integral with respect to a Brownian motion that we will note W. So to obtain an explicit expression for this process m bar, the only thing to do is to compute its quadratic variation, which can be written as the limit of that of Mn, which can be obtained directly. So, a priori, m bar should satisfy this kind of equality. And what we do now is that we write this rescaled sum as a function f integrated with respect to the measure mu bar ns, which is the empirical measure of the n-first coordinates of the limit system. Now, if we assume that this sequence of empirical measures mu bar n converges to some limit measure that we will note mu, we will know that the limit process m bar should have this form. And so the limit equation should have this one. So now, to end our heuristic, let us give some properties that mu satisfies. So according to our previous reasoning, we know that mu is the limit of the empirical measures of the limit system, which is an exchangeable and an infinite system. So according to classical results about exchangeability, we know that mu is what is called the directing measure of the system. In particular, it exists, it is unique, and can be characterized by what is written inside the parenthesis. That is, conditionally on the directing measure mu, the coordinates of the system are IID mu distributed. And another thing that can be said about the directing measure of a limit system, of an exchangeable system, is that if we find a sigma field such that conditional to the sigma field, the coordinates are IID, it implies that the directing measure of the system can be written as a conditional law of any coordinate given the sigma field. And what we can observe in our limit system is the fact that the Brownian motion W that appears in the equations is the same for all the coordinates. And so this W is a common noise in our limit system. And this is why we need to condition by W to make the coordinate IID. And so the directed measure should be the law of any coordinate given the W. In particular, we can replace this multi-f in the equations explicitly by a conditional expectation given W. So now we have an explicit expression for a limit equation. One problem is that it's not standard at all, because we can say of it to be a conditional Makin-Blasov equation, because here we have a coefficient that depends on the conditional law of the solution of the equation. So natural question that can be asked is this equation well posed? So the answer is yes under suitable assumptions. Here I won't prove the well posedness, but I can give you a general condition under which we can guarantee it. So the condition is this one. If you consider a function f that is C1 bounded, lower bounded, and such that the derivative satisfies this kind of inequality. In this case, we can prove the well posedness of the previous equation. And what's interesting in this kind of function is that it allows to consider a function f of the following form. And to understand why this function f is interesting in a neural model, let me recall that the function f gives the spike rate of a neuron as a function of its potential. And so this kind of function can be interpreted in the following way. When the potential x and I of a neuron is bigger than some value x0, it means that the spike rate of the neuron is close to its maximal value. And so the neuron is active. On the contrary, when x and I is smaller than x0, it means that the spike rate is close to its minimal value, which can be chosen close to 0. And so the neuron is inactive, in the sense that there is very small chance that it sends a spike. Okay, so now let me show you some simulation of trajectories of the process xn1, which models the potential of one neuron in a network of n neurons. And we can see on the right picture the time intervals when the neuron is active and when it is inactive. And you can also deduce from that the spike time of the neuron, which is the time at which the neuron goes from active to inactive, because of this reset jump that forces the potential to jump to 0. Okay, so now let me speak about the main part of this talk, which is the convergence of the system Xn to the system X bar. So it's the convergent in distribution in coordinate space, which is D. So the space of Kardec function endowed with an appropriate topology. So what is not? So this is basically typically the kind of results that we call the conditional proportion of chaos, because here the limit system is not IID but only conditionally IID, because of this Brownian motion that is what is a common noise in this limit system. So what's not really convenient in this convergence is the fact that the size of the system Xn is n, which is a parameter that goes to infinity. So instead of looking directly to this convergence, we study another one, which is equivalent, which is the convergence of the empirical measure μn of Xn to the directing measure mu of X bar. Convergence still in distribution, and now in the space P of D, so which is a space of probability measures on D, endowed with the topology of the weak convergence. So to prove this convergence distribution, we do a two-step procedure that is classical. The first step consists in showing that the sequence μn is tight, and the second one, that all the converging subsequences of μn have the same limit. So here I won't speak of the first step because it's really classical. It's actually a consequence more or less straightforward of Aldous criterion. So we just speak about the second step, where we show that any limit of μn in distribution is solution of a martingale problem. So to formulate our martingale problem, let us consider Q in P of D. So here Q represents the law of the directing measure of the limit system. And we formulate our martingale problem on this canonical space, omega equals P of D times D square, meaning that an atomic element is composed of 3 random variables, mu, which is a law on D, and 2 Kaldek processes, Y1 and Y2. So what has to be kept in mind to understand the form of this martingale problem is that mu represents the directing measure of the limit system, and Y1 and Y2 represents 2 different coordinates of the limit system. For example, you can keep in mind that Y1 equals X bar 1 and Y2 equals X bar 2, for example. So the structure that we want on this space omega is that conditionally on mu, Y1 and Y2 are IID mu distributed. So we will undo this space omega with this probability measures P, which means exactly that mu, which corresponds to the set I, is Q distributed, and conditionally on mu equals M, Y1 and Y2 are IID M distributed, which is exactly the structure that we want. Then we say that Q is solution to the martingale problem if for all function G that is smooth enough, the process GYT minus GY0 minus integral of some generator is a martingale, where the form of the generator L will reflect the form of the limit equation. So let me recall it just here to make it clear. And the expression of the generator is this one. So in this expression, there are some terms, and each term corresponds to a term of the limit equation. For example, here the two first terms, which are the first order partial derivatives terms, correspond to the drift term. Then the second order partial derivatives term correspond to the Brownian term, and the term of the second line to the John term of the limit equation. Now there is now let me explain a point that I've not explained yet, which is why in this martingale problem do we consider two different coordinates of the limit system, Y1 and Y2, and why not just one? Actually, it's because we want to be able to recover from the form of this generator the interactions that exist in the limit system. In other words, we want to be able to read in this expression the correlations between two different particles of the limit system. So the interaction that we want to be able to recover is the fact that the Brownian motion W that appears in the equation is the same for all the coordinates. And you can see this property on the blue term of the generator, because you can see in this term that the coefficient that corresponds to the diagonal derivatives and the coefficient that corresponds to the cross derivatives is always the same. It's always the sigma square of 2 times mf. And this is what implies the underlying Brownian motions is necessarily the same for both particles. Because, for example, if we had two independent Brownian motions, so one for each particle, then the coefficient of the cross derivative should have been 0, which is not the case here. So now to prove our convergence of mu into mu, we just need to prove two properties of this martingale problem. The first one is that there is a unique solution to this problem, which is the law of the directing measure of the limit system. And the second one is that any limit of subsequence of mu(n) is solution to this martingale problem in distribution. So I won't speak very much about the first property because it is the most natural, since we have constructed this martingale problem from the form of the limit equation in such a way that it was possible to recover all the information of the limit system. So here, if we consider Q any solution of this martingale problem, we can reconstruct the limit system from the form of this generator. And so we can prove that Q is necessarily the law of the directing measure of the limit system. So this is the only solution, the only possible solution of this martingale problem. So now let me just speak about the second property, which is this one. If you consider mu a limit of a subsequence of mu(n), then the law of mu is solution to the martingale problem. That is, the expectation of f of mu has to be 0 for any function f of this form. So here the form of the function f is more or less classical, because what we want to prove is that some process is a martingale. So here in front of the bracket, we have the dependency with respect to the path of the process. So let's say what happened before some time s. And in the brackets, we have the increasing of the process between s and t that depends on the generator L. So to study this kind of function, we need to recall what is the generator. So let me do it here with the drift terms, the jump terms, and the Brownian term. And now to prove that the expression of mu is 0, what we do is that we prove that the expectation of f of mu n vanishes as n goes to infinity. So we need to write what is f of mu n, and we write it differently using the fact that mu n is the empirical measure of the n-particle system Xn. In particular, this integral with respect to mu n times mu n can be written explicitly as a rescaled double sum, precisely like this. And now, to prove that the expectation of this expression vanishes, what we do is to write differently the first term in the brackets. So the term in phi xnt minus phi xns, here, in the top right. We write it differently using Ito's formula, what would make appear the different terms of the limit equation, of the equation of xni, xnj. So there will be the drift terms, the reset jump terms, and the Brownian term. And then the goal is to compare term by term each term that comes from Ito's formula with its corresponding term from the generator of the martingale problem, which are the terms on this slide in color. So basically, we'll compare the drift term, the drift terms between them, the reset jump terms between them, and the small jump term that comes from Ito's formula with the Brownian terms that is here, that comes from the generator. And you can show that for each term, the difference between the two corresponding terms always vanishes as n goes to infinity, which shows that the expression of f of mu n vanishes. And recalling that mu is limit of a subsequence of mu n in distribution, it implies that the expectation of f of mu is 0. And so the law of mu is solution to the martingale problem. So here, I won't show you the precise computation about when you compare the corresponding terms. But the only one that is not completely straightforward is for the blue term, when you compare the small jump term with the Brownian term. And this computation mostly relies on Taylor-Lagrange inequality. So this is not really complicated to do. So let me just recall so here we have seen all the main steps to prove the convergence of mu n to mu. So let me just recall this proof here to make it clear. So in the first time, we have seen that the sequence mu n was tight. Then to prove its convergence, we consider mu a limit of convergence subsequence of mu n. What we have just seen is that the law of mu is solution to the martingale problem. And what we have seen earlier is that the unique solution of this martingale problem is the law, of the directing measure of the limit system. So, as the sequence mu n is tight, it implies that mu n converges to its only possible limit. So let me just send out some references. So the first one is articles that I used to do this talk. And the second one is a course about exchangeability by Aldous. And the references on the second slide are the ones that I've stated in the introduction. So I studied the same kind of question about propagation of chaos or conditional propagation of chaos in similar framework. So either in linear scaling or in diffusive scaling, so whenever n or whenever square root of n, and either with a reset jump term or without it. So that's why there are some variations. So thank you for your attention, and don't hesitate if you have any question.
Okay, thank you, Xavier, for a great talk. So as he said, do not hesitate to raise your hand. Seems Quentin has raised his hand, right?
Yes, I've got a question. May you re-explain how you derive the mean field limit and the integral with respect to the Brownian motion? I guess you said that you use an auxiliary particle system. That's right, or not?
For the heuristic part?
At the beginning of the sections, you explain us how you derive formally the mean field equation.
Yes. Should be there or?
Yes, just before, I think.
Okay, this one.
Yeah, so basically, how do you, can you re-explain why the blue term here is converging to the integral with respect to Brownian motion?
Okay, so actually, the blue term is more or less the same as Mn. So here I just speak about Mn.
Okay.
Because it's a bit more simple because the blue term depends on I because of this thing, the sum. And Mn doesn't depend on I. That's why I prefer to speak about Mn.
Ah, okay, the only difference, okay, understood.
Yes. Yes,
Okay.
so basically, they have the same limit if it exists. So for this Mn, we know that, well, we can prove that it's a discontinuous local martingale. And its jump height, which is vanishing because they have the form 1 over square root of n. So its limit should be still a local martingale as the limit of local martingale, and it should be continuous because the height of the jump vanishes.
Mm-hmm.
So as continuous local martingale, it can be written as an integral with respect to a Brownian motion. So now the question is, what is the integrand? So what we put here? Here it's just the square root of its quadratic variation. So the only thing to do is to compute the quadratic variation of m bar. So we write it as the limit of that of mn, and for that of mn we can compute this directly. So here, the only difference here is that we use system x bar instead of system xn.
But UG of S is one. No, sorry. UG of S is equal to what?
Which one? These are the height of the height of the jump is are the form u over square root of n, where u are random variables.
Okay.
So these are the height of the jump, partly. The height of the jump is UGS over square root of n. So G is the neuron is the index of the neuron that has emitted the spike, and S the jump time.
Okay. Thank you. Thank you very much.
You're welcome.
Okay, Etienne, you have a question?
Yes, it's better with the microphone. Thank you, Xavier. I have a question related to the question, to the end of your answer. The processes UJ are given, or are they related to the process XI, or the law of XI, or whatever? Well,
actually, technically, when the question is formulated with this UJT, it's not completely well posed. But actually, it's a part of the point process. So here, to make it for formal formulation, what we have to do is to write the point processes as thinning of Poisson measure. And these UJ are given by these Poisson measures. I don't know if it's really clear.
Should be.
So, can you repeat your question?
No, I'm not sure to understand if UJ is given and you put it in the dynamic of the vector x, or if UJ, I see that DZ depends on the jump of x, but the size of the jump UJ when xi has a big jump, I'm not sure to understand if this UJ of t depends or not on xi, the law of x, or whatever.
No, it does not depend on anything.
Okay, and my question was, what can you say if the interaction are not independent, so are correlated with
so if
the state of the network?
If you consider it as a function of xn, a function of
yes, for instance, yes.
Yes, so this another works I've done also with Eva and Dasha.
Uh-huh.
Well, in this other work, it really depends on the potential of the neuron that has emitted the spike, the neurons that received the spike, and about two random variables. One created by the ones that emitted the spike, so one UJ, and another UK, let's say, for the ones that receive the spike. In this case, we also prove similar results, but the limit system is less classical. And what we obtain is that instead of having Brownian motion at the limit, we obtain white noises because of the form of the interaction that are more complicated.
Fine, thank you.
I'm not sure if Quentin has an additional question. No, huh? Forgot to raise. Okay.
Sorry.
Okay, it seems that we have no further questions. So with this, I will thank Xavier and all the participants of this mini symposium. And then hopefully I will see you or hear you tomorrow. Goodbye and have a great day.
Thanks for organizing this, Roman. Bye.
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 Thank you, Ramin.